A very special type of density curve that is used for many applications in statistics is called a normal distribution. Normal distributions are a class of unimodal and symmetric density curves that are very important in statistics. So we're going to look at an example. According to the CDC, which I believe is the Center for Disease Control, the heights of 12-year-old males are approximately normally distributed, that's important to remember, with a mean of 149 centimeters and a standard deviation of 8 centimeters. That means that these heights are distributed in a unimodal and a symmetric way that can be modeled by a normal curve. So we're going to learn how to sketch a normal model and label it and some characteristics of a normal model. So first of all, a normal model has two parameters. And a parameter is just a numerical description of the particular curve. So the parameters here are the mean, mu, and the standard deviation, sigma. So in this case, we use the notation a capital N, and in parentheses we put the mean, and then comma, and then the standard deviation. So when you see that notation, that means we're talking about a normal distribution with this mean and the standard deviation. Now to draw this, I start by making my x-axis, which has the values of the data on it. So I'm going to start by marking right in the center 149. That is the mean. And I'm going to put the top of my curve right above that mean. And then I'm going to mark 3 marks to the right, equally spaced, and 3 marks to the left, equally spaced, to represent 1, 2, and 3 standard deviations from the mean. So 149 is mu. Then we're going to do mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. So we're going to add 1, 2, and 3 standard deviations to the mean. So if we add 8 to 149, we get 157. We add 8 again, we get 165. We add 8 again, we get 173. Now we're going to do, on the other side, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So if we subtract 8, we're going to have 141, 133, and 125. Now to draw the curve, I want you to make a dot above the mu plus sigma and mu minus sigma about halfway up to where the other dot is. So about right here and right here. And when we draw the curve, what happens is this point above the 1 standard deviation mark is a point of inflection in the curve. In other words, as I draw this, it curves down into that point and then it curves back up. So it kind of curves down and then curves up. And notice that it smooths out to be very close to the x-axis. By the time we get to 3 standard deviations, it's very close to the x-axis. As a matter of fact, I probably drew this slightly too high. It's probably more like that. So kind of erase down a little. Let me just redraw that one. It's hard to draw these very, very well, to be honest. They're really difficult to draw. But we should see that by the time we get to 3 standard deviations, we're almost at the x-axis here. And then I'm going to give this a title because you should always title your graphs. So here we're going to say this is the heights of 12-year-old males, and then the units in centimeters. So what that tells me is what these numbers down here represent. Now we remember that the area under the curve of any density curve is 1 or 100%. But the normal curve has some particular characteristics that are very helpful. With a normal curve, we always know certain percentages of the data that fall into certain regions of the graph. For example, if we look at the region here within 1 standard deviation of the mean, 68% of the data, or the curve, is between 1 and -1 standard deviations from the mean. 95% of the data lies within 2 standard deviations of the mean. And 99.7% of the data lies within 3 standard deviations of the mean. This is known as big drum roll, the 68, 95, 99.7 rule. How about that? Named so that you can remember the name. It's also sometimes known as the empirical rule, but this name has kind of stuck because if you remember the name, you remember the rule. And what this rule says is that if data is approximately normally distributed, in other words, it has a unimodal and symmetric shape, then 68% of the data, and I should probably say approximately, let's go back there, then approximately 68% of the data lies within plus or minus 1 standard deviation of the mean. Now, to avoid writing that whole sentence again, I'm just going to say 95% within plus or minus 2 standard deviations and 99.7% within plus or minus 3 standard deviations. So as long as we have exact numbers of standard deviations from the mean, plus or minus 1, 2, or 3, we can approximate the probability of data falling within that region. So let's look at a couple of examples. First question, about what percentage of 12-year-old boys will be over 157 centimeters tall? So whenever you have a problem like this, you're going to start by naming your model. So I'm going to put the 140, the normal model with those parameters. I'm going to make a sketch of my model. I'm going to mark the particular boundary line here that I'm looking at, which is 157 centimeters. This happens to be at 1 standard deviation above the mean, so I know it's about right here. And I'm going to shade the area that I am trying to find, and this would be the area above. So this is the area I am trying to find here. And then I'm going to use my, since this falls exactly 1 standard deviation from the mean, I can use the 68, 95, 99.7 rule to figure out what area that is. So what I know is that 68% of the data lies within 1 standard deviation of the mean, which means that everything outside that center area must be 32%. And in particular, this half then would be 16%. So I can say then that the probability that x is greater than 157 is equal to 0.16 or 16%. In the second example, I want to know between 133 and 141. So notice here, 133 is 2 standard deviations from the mean in the negative direction, and 141 is 1 standard deviation from the mean in the negative direction. So I have my normal model still, the same parameters that I had before. Okay, and if I sketch my model here, so this is about 141 and this is about 133, and I'm looking for the area in the shaded region right here. Well, if I were to look at the symmetry of this, I know that this section in here has 98% of the data, and if I go from here to here with the 2 standard deviations, this would be 95. So 95, I drew that arrow out a little bit too far here, probably not quite that far out, but 95 minus 68 then would give me the area in here or in here. So this would be 95 minus 68, which equals 27. So 27% falls in either this region or this region, and then half of that would be just in the left-hand side. Half of 27 is 13.5, or 13.5% here. So I can say then that the probability that 133 is less than x is less than 141 is equal to 0.135 or 13.5%. Now let's look at one that goes a little in kind of backwards from that. Let's say we know that the middle 95% of the scores of or suppose that a distribution of test scores is approximately normal and the middle 95% of the scores are between 72 and 84. What are the mean and standard deviation? So if I draw this here, this is what I'm looking for now are the mean and the standard deviation. That's supposed to be a question mark here. I don't know what either of those are, but I know that two standard deviations to the mean are 72 and 84, and that this then would be the 95%. I know it's two standard deviations because I know that's 95%. So what I'm looking for is what's halfway in between. Well, halfway in between 72 and 84, since there's a distance of 12 here, then this would be 6 and this would be 6, so this would be 78. And then I want to know what one standard deviation is. That would be this value right in here. So since this is 6, then this is going to be 3. So the standard deviation is 3. So this would be 78 and this would be 3. Now, looking at the same example, could I calculate the percent of scores that are above 80? So here would be what I'm saying is 80. Actually, that's not a good drawing probably. We know that one standard deviation above the mean is 81 because that would be 3 bigger than 78. So I'm looking for anything above 80. I'm be looking for these values here, above 80. Could I figure that out? No, I don't have any rule that tells me what percentage is above 80. I mean, I could make some sort of guess here, but realize this is a curve here, so it's not like 1/3 of the way to that this is 1/3 of half of 68. I really don't have any rule for this, so at this point, no. The 68, 95, 99.7% rule only applies to plus or minus 1, 2, or 3 standard deviations. It doesn't work for anything in between. So we are going to learn how to do this, but it's going to take a different technique. Okay, let's look at one more thing before we end this, is how well, now we looked at a perfectly curved distribution. We said this is true for any normal distribution, but what if we have real data? How well does the 68, 95, 99.7 rule describe this data? So we can see that we could use a normal model to approximate this data. It looks like a fairly normal curve here. We see that the mean of the distribution is 76.4 and the standard deviation is 7.9. There are 50 students, so there's 50 dots here, making it easy to count. So the question is, if we were using this mean and standard deviation, let's find the boundaries of plus or minus 1, 2, and 3 standard deviations from the mean using what we have here. So in other words, I'm going to do 76.4 plus or minus 7.9, 76.4 plus or minus 2 times 7.9, and 76.4 plus or minus 3 times 7.9. So it turns out that this would be 68.5 to 84.3. This is 60.6 to 92.2. And this is 52.7 to 100.1. So those are our boundary lines for 1, 2, and 3 standard deviations above the mean if I were to draw my normal model and write those in. So let's mark these on the graph. Each tick mark represents 2. So 68.5, this would be 62, 64, 66, 68. Looks like this dot right here is probably at 69, so we could draw our 68.5 right here. And then 84.3, it's 82, 84, 84.3 is about right here. So how many of the dots are in between plus or minus 1 standard deviation from the mean? So if I'm going to count the ones that are outside and subtract from 50 because that'll be faster. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 are outside. So there's 33 dots from here to here. So 33 out of 50 then would be 66%. Now let's look at 60.6. 60.6, this looks like it's 61 here. So 60.6 is probably right here. So that dot would be inside the boundary. 92.2 is about right here. So we notice there's only 2 dots outside that boundary. So there's 48 out of the 50 that are inside. That would be 96%. Now if we mark 52.7 and 100.1, we see that all of the dots, or 50 out of 50, 100% are inside here. Now that's not exactly 68, 95, and 99.7, but it's awfully close. So we can say that a normal model, the rule, the 68, 99, 95, 99.7 rule, is a good approximation for data that is approximately normally distributed. It will never be exact, but statistics is about probabilities, not about being exact. So this is a good representation, a good estimate of the percent of the data in these various categories.